Thank you everybody for your patience getting started. I've been in the mountain time zone for the last 5 days, and I think my brain's still an hour short. So
Everybody's stuck in traffic anyway.
that's what I'm gathering, because I pulled up and went, wow, I wonder if I did get the email on time, which I didn't as well. So hopefully you guys are all doing fantastic. Just want to say welcome to all members and new friends to our organization, as well as anybody thinking about joining. It's a fantastic group we have. Today is October 18th, and this is our October monthly member meeting. We have one of these every month. Something pretty cool happened the other day. On the lower right could actually be the moon tonight. As I was driving in, I'm like, hey, that kind of looks like my eclipse picture, but that's what the eclipse looked like in just outside of Denver, Colorado. So they got about 80% eclipse there, so or 80% coverage. So some cool things happened in the sky over the last month. So we'll go ahead and get everything rolling tonight. First off, I know we sent out the reflector with the member meetings minute, and as well as the board meetings, board minutes in it. Does anybody have any questions about anything that has been going on with the minutes? All right, good deal. Keith usually has our member number for us, but he's not going to be here. We are currently at 162 members, and I believe that he's going through and going to send out for dues, I think, coming up shortly. And Theo is also out. She sent an email saying she won't be here because she's enjoying the dark skies of New Mexico. But we have in her email, she said we have a little bit of money, which is classic. In our bank account, we have $8,240.45. And let's see, I'm trying to think. I know we have, she just transferred a lot of money out of PayPal. We also just purchased some solar glasses, which I have here in the box. I know the eclipse was last weekend, but we have another somewhat important eclipse coming up in April. And so every member gets 2 pairs, and then for members, it's an extra $1 a pair if you want extras, which is a pretty good deal. So we've got a handful of glasses up here. If you're interested, come see me. But I'll pretty much be bringing them to every member meeting from here till we're out, I guess. So if you have a need for solar glasses, let us know. All right, so we also have loaner equipment available as one of the perks for member meetings or for membership. I need to get our Google group list updated, but if you're interested in the scope or are thinking about buying a scope, check out what we have, and we may be able to get something that you're interested in so you can play with it before you buy it, and get used to knowing whether you'd like to use it and figure out how you'd use it. Do you use it in your yard? Do you travel with it? Things like that. I don't know if that reverb's coming from me. But if you do have one of our scopes, let us know how it's going. Let us know if there's anything we can help you with in terms of maybe you just can't get it aligned, or something's not as in focus as you think. Maybe there's something we can help with there. You can find us at bsasnashville.com. This is the website from 2 hours ago. Nice little image here of the clear sky chart. It seemed to be pretty clear out there right now, and so nice dark skies, which would be good if you plan on going out tonight. The moon isn't too bright, but at least we don't have any clouds for tonight, knock on wood. But tomorrow I think we're supposed to get some storms in, so you can see it kind of brighter on tomorrow in terms of seeing and brightness. On the website you can find the upcoming star parties, as well as meeting event or meeting information. We also have posters for sale if you're a hatch print fanatic. These are pretty cool. We had them printed up a couple of years ago, I believe it was now. And they built a stencil just for us with that telescope at the bottom. So it's pretty unique, especially if you collect hatch prints. Our Facebook group, we post a lot of really cool content here. Theo is the one that usually is posting, and she's in New Mexico. So we still have some pretty cool stuff on here. Hopefully we'll get an update on what clear sky looks like in New Mexico, right, where she's getting some really cool images right now. This is what we saw at Pickett last month. Still beautiful skies there. On Twitter, this is a post that we recently shared of I tried to get it to save the GIF, right, of the moon shadow actually crossing over. But this is at the back end of it. So like the Nevada is starting to light up as it's coming across. So it was pretty cool watching that GIF. And so if you're interested in seeing it, hop on Twitter and check that out. Instagram, Steve, thank you again for running this for us. As should be quite a few pictures of our Ring of Fire eclipse showing up. A lot of different flavors, a lot of different colors. It's fantastic. It was a pretty cool event. Hopefully you guys got to see it here. What was weather like? Was weather all right here? No, partly cloudy. You know, I was joking with my wife. I was bummed whenever I found out that our vacation fell on the weekend of the eclipse. And I'm like, oh man. She goes, well, you can stay. And I'm like, let me check. And I look, I'm like, oh, well, yeah, 80% up there. Yeah, well, okay, I'll go. And then I started seeing pictures roll in from here and they look kind of clouded. So like almost fortuitous. So I felt bad.
Well, I tried the eclipse glass here between clouds and it worked.
Oh, nice. Nice.
I'm not blind.
Not blind. So they do work. So we didn't get the knockoffs this time. So good deal. But so if you're interested in showcasing some of your pictures, especially of the eclipse or anything you find interesting that you think the group would enjoy, feel free to share it with us at info@bsasnashville.com, or you can share it to Google Groups and we can get it put up on Instagram. Speaking of our Google Groups, there's a lot of activity going on right now, which is awesome. We're starting to pick up the speed again now that we're kind of a year post-COVID. The action boards are starting to light up. We have a lot of information on here. People sending out requests for people coming out to star parties. We have pictures coming through. See, Theo posted her eclipse from New Mexico here. We have a lot of really good content. Here's Bud's picture from the solar eclipse. I thought this was really cool because it's a pretty nifty setup. Nobody has to burn anybody's eyes. Don't have to look towards the sun. You get a kind of nice look towards the ground. So it actually turned out really cool. It's pretty cool, Bud. And so if you're a member and don't have access to the Google Groups, send us an email at info@bsasnashville.com and we'll get you in there. Otherwise, anytime you want to post to the group, you can just submit there and everybody will get a blast email. It's a good way to communicate on anything going on in regards to the night sky. Speaking of night sky, we run our organization through the Night Sky Network. And if you're interested in membership, you'll go through here and you'll register. And then you'll go to our website and pay your dues, which is relatively cheap for membership. But again, we run everything through the Night Sky Network. And the Night Sky Network is this amazing wealth of information where they have a lot of outreach materials. They didn't change the October thing from last year where they're looking at Jupiter's moons and talking about the Clipper, the visit to the moons. Pick up some really cool information from these articles like Io, Europa, Ganymede, and Callisto in order of distance from Jupiter. I eat green caterpillars. I never knew that. So it's going to stick in my brain for a while now. Also, kind of required, they had to celebrate our marvelous moon article as well, where you can look at the moon phases and festivals that are happening between now and April. And in my brain, I'm thinking April is a ways off, but it's only like 5 months. Is that right? 6 months-ish. And so my brain is like trying to ponder that. So, because I started counting the moons in between, and April 2024 is coming up quicker than I thought. So there's some cool things happening. Coming up next is the International Observe the Moon Night on the 21st. And so do yourself a favor, hop out, take a look at our moon. Apparently a lot of other people are as well. Also on the Night Sky Network, they have a cool segment of what's in the sky. I was out till I guess it'd be 3 a.m. 2 nights ago, and I saw big, beautiful Orion come up, Pleiades sitting beautiful, Jupiter just off to the side. I have them on top of trees like little stars, managed to line up perfectly. I'm sure I'll post that up, see if I can get that on Instagram. But Orion is starting to come up before dawn. If you're interested in going to star parties for the to the public star parties to share information, to interact with the public, share our wonderful interests. They have outreach resources as well. And so you can kind of take a look at that and, grab a cool tidbit to share with people, like what's up in the sky, during this time of year. Let's see, since our last meeting, we've had a few events happen. There was a private star party, I believe at Ron's house. Was there a lot of attendance there? I think I saw some pictures from it. Yeah.
Probably
10 to 12 people. That's really awesome. And I believe there's another one coming up. Is that what I saw?
Yes, double star party begin this weekend. So Friday, Friday, another private party runs, and then we got the public on Saturday.
Gotcha. Good deal. If anybody's interested in a private party, send us an email or get on the Google groups. Yeah, see Steve afterwards. On the 23rd, we had a public star party at Mill Ridge Park. It's very well lit. We did see, from what I hear, we did see a good moon, and saw a few planets there. But it was still good for outreach. Thank you to Mill Ridge for hosting. It was a good, it would seem to be, we had a decent turnout for it. So that was good. The October 14th, which was the day of the eclipse, I wasn't in town. Did that happen? Did anybody go to that? I haven't heard one way or another if that one actually held. But that was what was scheduled officially. Upcoming, so this weekend coming up, we have a public star party at Bell's Bend, starting at 7, and sunset hits at 6:03 p.m. And then I put this up here because it's the next thing in order. November 5th, we set our clocks back 1 hour, and so that means that everything gets shifted, because as I was looking at our schedule of star parties, our next private star party scheduled is November 11th, and sunsets at 4:42. I went, that's odd, and then I went, oh, time change. So like night sky, we can get out there early now, right? And not get in trouble for missing dinner. So private star party November 11th at Water Valley Overlook, and that's classically where we have our darkest skies near Ron's house, and Ron's been hosting some of these as well. So not going to impose on that, but we do have access to Water Valley. If you go out to Water Valley, be sure you have a permit that's available on our Google groups. Our next member meeting is November 15th. It'll be here at 7:30. And then the weekend after that meeting, there's a public star party on Warner Park. So you can put that on your calendar if you're interested in that. Coming up in the night sky, 14th was the annular eclipse, which was pretty awesome if you saw it. Coming up on the 21st, a couple days from now, the Orion and meteor shower, usually a pretty good one, not the 500 meteors an hour that they always say, but if you get some decent skies, you can pick up a few. Venus is starting to move out to the west. We get full moon and Jupiter on the 28th, and then November, we start to see some cool things with the moon and Venus kind of coming closer together. You get the lean in meteor showers and so on and so forth. So if you like looking at things coming together from the stellariumweb.org site, you can see the moon and Venus kind of sitting there, two decently bright objects, should photograph well if you like kind of looking at those conjunction things. And then the Leonid meteor shower, I just did a real quick Google search and I found the Great Leonid meteor shower storm of 1966. So I thought it was a very well done photograph. So who knows how many you'll see, but the key to finding good meteors is find nice clear skies and dark skies. So if you can get out to some dark skies for these meteor showers, it's probably the best. All right. Any questions in terms of business for the the club. Kind of ran through it quick because I know I was running. All right. Well, without further ado, tonight's speaker, we have a couple people here from the Vanderbilt Aerospace Design Laboratory. Do you guys like calling yourself the Vanderbilt Rocket Team? How do you guys have the Vanderbilt Rocket Team? That seems cool. We should get t-shirts. I know I've been in contact with Andrew. He brought some friends along. I'll let them introduce themselves as they're up here with you. If you guys want to come on up. Left, right, perfect. Yep. Thank you. Speaker view if you have any notes on
The
that.
slides are just appended.
Yep.
Awesome.
Go for it.
Thank you. Hi, everyone. I'm Andrew. You guys want to introduce me?
Yeah. Hey, I'm Aziz.
And I'm Sebastian.
Yeah, so I'm a current graduate student in this lab at Vanderbilt, and they're both seniors working on this year's project. So I just wanted to give you guys kind of like an overview of what our lab does, kind of its goals, why it was founded. And then I was on the team last year. It's mostly a senior capstone project thing. So I'll dive a little bit into our project last year and take some questions on that if you guys would like, and then they can talk about their project and what they're working on right now. So yeah, I'll start with kind of the mission of the ADL, then our project, and then some of our like student outcomes and things like that. So our mission, we were founded in 2007 by this professor, Dr. Anil Kumar at Vanderbilt, and he pointed out when we asked him kind of why he started this program, was, in his opinion, some concerning trends in engineering and kind of engineering education nowadays. And that's overall lack of hands-on training, and that just lack of hands-on experience leads to students that aren't very confident in their abilities. And besides that, a lot of talent leaves the engineering industry to go to consulting, to go to other things, which nothing inherently wrong with that, but trying to bring some of that talent back to engineering, as well as kind of the design to approach in production. I think our generation kind of grew up out of NASA's heyday and kind of the peak of space exploration and all that, and grew up more with like SpaceX time, and the way that these newer engineering companies approach design is very different from the way NASA does it. And in his opinion, we have some things to learn from the past. So on that, our goal is very much experiential learning for students and undergrads. So translate all our theory in classes into a real product and hopefully become more competent and confident engineers. Yeah, so on that, this is our advisor for the lab. Was founded in 2007, very bright guy, went to the University of Madras in India, and then Caltech, NASA, and worked on some space shuttle missions at NASA. And he started this program in 2007 at Vanderbilt. And to this day, we still don't have an aerospace program. So we're just in the mechanical engineering department, but he's kind of carved out a nice little niche for everyone to operate. So the main function of the lab is NASA's University Student Launch Initiative. So NASA every year puts out a challenge for universities, and it's a competition between about 50 teams. So they give you a payload challenge, and all these teams compete. And then in April, we all go to Huntsville and we fly our payload. You write a lot of reports and all that, and they declare a winner. So we've won. We did not win last year, unfortunately, but we've won 7 times in 16 years. So good record. We're trying to bring it back this year. So that's the main function of the lab. And then kind of secondary function is graduate research and mentorship and community outreach and things like that. So I'm a first-year grad student. So we have different partnerships. One is with NASA. We have a naval project that I'm working on, and that's just kind of next progression in the system. Additionally, we do a lot of community outreach. It's a NASA requirement, and it's something that we'd like to try and go above and beyond on. So last year, I think we had like 1,400 people. We hosted like 20-something events, which was fun. So that was at Dyer Observatory, and then local natural MPS schools, and then basically any event that will host you, we try to pop up at. Yeah, I'll dive in. This is our project from last year. So NASA's challenged us, I guess, step back a little bit, kind of motivate this. I think the reason I fell into this stuff is last year with like the Webb telescope and everything, and all these incredible advancements that we have in technology and the scale of NASA's projects. Part of the value we wanted to get from this experience is what does it take to deliver a payload like that to space, and kind of the challenges that entails, because that's something that you always know is hard. You say like rocket science and all that, but we want to develop kind of that skill and that way of thinking. So NASA's mission that they set out was basically they're going to transmit radio commands. So you have to launch this rocket, come down under a parachute, and then after you land, you have to receive radio commands, and everything has to happen autonomously. So you have a little robot that pops out and swivels around, takes pictures, and then save those pictures. So that was the challenge they put out, and our kind of overview of how we approached it. Year to year it changes. Sometimes, like their project, in my opinion, is a little more interesting. It's in flight, but all of ours are post landing. So we go up, we come down to two parachutes here. We detach the parachute so that the wind doesn't drag you whatever 20 miles, and you get nice clean pictures. So we have to detach the parachute, and then this whole central part of the rocket can rotate. So we rotate so that our camera is facing upright, and then we have this little, kind of works like a step ladder, like a extendable ladder. So we have a little ladder system that's motor driven, comes up and then looks around and takes pictures. I won't dive into all the numbers, but rocket was roughly 10 feet, 50 pounds ish. So it was a big rocket, and went about 4,500 feet. And part of NASA competition is you get scored based on how close you are to a target altitude. So we didn't win the overall competition, but we did win that award of hitting 4,500 pretty much on the dot. And for that, we had these, there's the primary spins of the rocket, and then also secondary payload that you don't get points for, but it was just our professor likes to throw in extra work. So we had a secondary project to slow down the rocket and really hone in on our target altitude. Yeah, this is everything that I mentioned before. So this is how it flies, and then after it lands, it'll separate. The parachute would be attached here, and you have a leg system so that you land nice and even, so that the whole rocket's level on the ground. Legs. This whole central section spins. We have 3 cameras around the body of the rocket and this lift system there. Feel free to interrupt me and ask questions as we go too, but that's our overview. So, yeah, these are a bunch of our slides, but basically the main things we want to emphasize throughout the project is safety, and kind of getting the mission done no matter what. So they say the Webb telescope had some like 600 failure points, from launch to extending those panels and all that. So if any one of those things goes wrong, then we don't get our nice pictures back here on Earth. So I'm trying to develop a sense for how to think like that. So this is our recovery system. We had some test flights, and the idea with this is you go full spectrum from the whiteboard work and simulations and modeling, and all kind of the drier stuff, to manufacturing, machining, and testing everything. So I just threw in this slide because there's a ton of kind of numerical analysis that goes in, just making sure that your rocket doesn't go 2 miles that way, and you can recover it nice and safely. You land within your radius. And then on the more hands-on side, I have some slides here of different subsystems. So pretty much everyone comes in pretty raw in terms of skills. We've done a couple of class projects and hobby projects, things like that. So this is kind of trial by fire, but this is a good example of kind of a lot of custom machine parts. Had to weld some parts and laser cut, water jet cut, kind of for everything to come together. So that's a skill that I'm definitely really grateful for, and trying to design and manufacturing everything with the idea that you have to test it and integrate as your next step. Yeah.
Who's building it? Are you building it?
Yes. Yeah. We build it all.
You're building all the stuff.
Yes.
These solid rocket booster?
Yes. Solid rocket motors. There's other competitions where people make their own motors and do hybrid and liquid motors. But NASA, for safety reasons, they just commercial off the shelf motors. Yeah, really? Yeah.
There's some that went up. I still don't know where they're at.
Yeah. Yeah. Vaporized up there. Yeah. Exactly. So that's why emphasis on the safety, because yeah, it's quite stressful.
So you don't mix your own fuel.
No, that is the commercial off the shelf part is exactly buying the fuel. I know. So that's this is one subsystem, and then I kind of run through. This is where the parachute detaches. So if any of you guys know how like glider planes work, you get towed behind a bigger plane, and then there's a little hook that releases you. So to release the parachute, we had a similar system because it has to take a ton of load, like 2,000 pounds, but then be able to kind of readily release with a tiny motor. So
you don't have a charge to pop the shit out?
that's how the parachute comes out, but then for detaching it from our vehicle after the fact. Good question. Yeah, so you use energetics, but then NASA doesn't let you use energetics down on the ground.
Those exploding rivets.
No, exactly. Can't be starting fires. So this is the system that we designed and got some good machining experience, and then you stick it in a load frame, pull it to failure, iterate on your materials, and learn a lot about
Use a kind of gyroscopic controls in the.
of the whole rocket.
Do it all spin stable. Spin,
Oh,
spin, stable.
yeah, no stabilization.
So it's all spin, I can't say that, spin.
Correct. No induced spin.
Spin.
Yes, that was actually, they worked on a summer project this year, which was roll control. So those fins that we use to slow down the rocket, we didn't actually get to test fly it because the timeline runway ran short, but it's all made and developed to basically spin the rocket and control that for extra stability and for other reasons. But yeah, all passive there. No reaction wheels or anything. Then next subsystem, so we land, we had our legs, we had the parachute detachment here. This is where the camera actually has to rotate. So this was kind of probably our most complicated system because you need something that's super strong structurally and axially. So as you fall, parachute yanks you at however many thousands of pounds. You can't come apart, but then we just have little motors in there, so you have to be able to spin and orient the whole payload. So it's a valuable, frustrating machining experience. But some good lessons learned with that one. And then once again, just some quick short videos of us testing it, making sure that it can lift the camera when if it comes out for some reason early and it's out at 90 degrees, you have to be able to rotate up because NASA wants nice, regular level pictures. Yeah, this was kind of the novelty in the situation in the project. So basically our advisor and just kind of the philosophy of the team, a big part of it is project selection. There are, in theory, easier ways to accomplish something like this, like you can have doors open and then you pop out an arm with a camera on it. But that has some drawbacks. Primarily that in theory, there's more failure points. You need a motor to unlock the doors, motor to lift. And if your camera doesn't come out, then you're kind of left without photos. So our idea was to leave the camera outside the vehicle kind of all the time so that should your motors fail, should something fail, you can still get pictures. And then we want elevation because obviously this wouldn't be the case on Mars or the moon, but in Huntsville, the year prior, there was a lot of grass, like 2 feet of grass. So we wanted to be able to lift up above that and get actual landscape pictures.
But you're setting up 3 cameras, so you're using 3 times the weight.
Yeah, that's correct. So 1 processor, but then three like little ArduCam kind of hobby cameras, nothing crazy. But yeah, correct. Which I'll get to some of our failure modes later. There's some risks associated with sending up 3 cameras there. So we did that in theory for redundancy. Should 1 camera fail, you have backups and you can spin, get to another one and get your pictures. So yeah, the way this worked was kind of cool. It was basically these linear guide rails, kind of like drawer sliders, and they were embedded in this like carbon fiber 3D printed material. And then you only need 1 actuator to get all that height. And basically there's a Kevlar cord that gets wound throughout the layers here and fixed on the end. So as you wind it up, it's kind of like a winch, and then you get your extension there.
Not inspired at all by R2D2.
No. And then another thing is interdisciplinary. So all of us here are mechanical engineers, but obviously a project like this requires a lot of interdisciplinary work, some electrical work, some computer science people. So we all get to work together, which is awesome. And Vanderbilt, I don't know if this is the case at schools in general nowadays, but from the circuits classes that we've taken, you don't do a lot of hands-on work. It's a lot of whiteboard. And the research at Vanderbilt is mostly focused on radiation and outer space. And a lot of people feel like they graduate and lack those hands-on skills. So this is something, especially for the electrical engineers, good practice of board design and board assembly, things like that. For when you get your first job, you actually want to be able to make things that work. So this is a quick video of the PCB. And the purpose of this one was it sat on top of our flight controller and basically had a bunch of different motor drivers on it, servo drivers, because we had like 8 little motors and things that needed to happen and connected to all the cameras. So that was that. And here's just kind of overview from design. So we do it all in CAD, computer-aided design. On the left there, airframe. We do a lot of custom parts. We buy some off-the-shelf parts and modify them for strength, and then build the whole tail section ourselves. And then these are all the components that we made. So a lot of carbon fiber and machining, and I think our CAD assembly had something like 1,000 parts. So
Y'all are fabricating at Vanderbilt.
yes. So there's like one undergrad machine shop class. You can see some of these parts are pretty ugly in there if you were to zoom in. So it's a learning experience for sure. But yeah, we made everything in-house, which is fun. And then here's the final thing on the pad, which was one of the best feelings, seeing it all come together.
Step up in cardboard tubes and also wood. I used to
Yeah,
try to restuff old fireworks for homemade gunpowder.
not it. Yeah, so we did some quick tests. You want to make sure here that your parachutes, this is what you were saying with the parachutes coming out energetics. So that's a deployment test, making sure our legs come out so that we land nice and level. Nothing too interesting here, just close up with some of the avionics and machine parts. Yeah.
So what kind of commands do you have to, or do you think it's totally autonomous, right?
Yes. So NASA had a set list of like 8 or so commands that we had to have programmed in, ready to receive.
When you say commands, I'm thinking you're sending commands up to it while it's in flight.
Gotcha.
Says something.
Yeah, so I guess the inspiration for this one, they kind of connected it to like the Mars rover. How like, I know it's every day when we're facing it, we send it something and then it goes the next day and executes it while we're sleeping. And then we come back and get the pictures back, ideally. So yeah, it's all post landing. They would send it a couple times to you. So
And make sure that you're doing it in metrics and not English.
yes, not crashing anything, no major system failures like that. So quick test flight. I'll try and pull this up and we can fast forward through it. Because it's a little redundant with what I just said, but let's see. I don't know if it'll go full screen, probably not, but I'll skip ahead to our. So. Yeah, it's all right. I'll pause. I just want to show you guys the commands there quick. So you just asked about what command we get. One is just 60 degrees one way, 60 degrees the other. Take a picture, obviously. And then just some basic, nothing crazy, no computer vision, anything like that, but super basic image filters. So grayscale, rotate images, some special effects. We did some like blur that's used in computer vision a lot, and then remove all your effects. So basically they want to test your software and they have to be able to stack and say grayscale 180, 60 degrees to the left, and then you get one picture from that.
Are you sending the pictures back to NASA?
They did not require that this year. They have in the past. I don't know why they.
Well, when you take a picture with your camera, it just gets saved to the camera.
Yes.
Okay, it does send it back.
Yeah, it does not. It does not. I think 2 years ago they had a project, and even this year there's a lot of issues with just like radio interference because everyone's new to ham radio and new to transmission. So they had people all on the same frequencies. They couldn't tell who was sending what, and I think it turned into a mess.
PL codes.
Yeah. I know nothing about it, to be honest. But I'll do that and then skip it ahead some more. Don't know if it'll work.
You
Yeah.
won't be able to,
Yeah.
Yeah.
So I want to show the flight video.
You exit the presentation mode?
Yeah.
Yeah, it just takes.
Yeah. I'll come back, but we have some quick flight videos in there, like our 6 test flights, which are more fun and interesting. So we'll come back to that. But some test flights, and then basically all that simulation we do early on, you want to get all your data, all your flight data, and see how good your simulations are, refine your models, or how your thing's gonna fly. So we get a couple things, mostly IMU data, so that's inertial measurement, all acceleration, gyroscope data. And then you can check out things like this is your theoretical motor performance curve. And then you can get your measured, your mass at every point in time. So you can get your actual measured, and in this case, the motor performed very well. And very small difference, as well as measuring your acceleration at different points in flight. So if we see that when the main parachute pops out here, we're at like 16 Gs of acceleration. So that helps kind of redesign anything. If it's too weak, you know how much force to expect under certain conditions. So you can kind of hone in on your safety factors a little bit. Other thing, I mentioned there's little fins that should slow us down and help us hit our target altitude. So this is some data from that we got. This is coefficient of drag here and over the time of the flight. So it's kind of a crazy plot, but if you just look at these dots, basically, so we have one drag coefficient that's decreasing, and then we deployed our things and you see a big jump. So you can see we like noticeably slowed down. So our system, after 2 test flights, finally did what we were looking for, which was rewarding. Yeah, so from all that data and the drag data, and you kind of go back, refine your model. So based on how much you weigh on the competition day and how fast the wind is going, we know what height we need to start controlling our altitude a little bit. And then, all right, competition. This is in April, towards the end of the year. So everything kind of from a distance looks like it went just perfectly. So went up, came down, landed safe. We landed on our 2 legs, nothing broke, which is great. And then when we kind of looked through some binoculars and we approached it, it looked like everything kind of rotated autonomously, lifted autonomously. But then we had some payload mission issues that we'll get to in a second. But yeah, these are in-flight photos of it going up, coming down, and then it landed with the main camera off to the side. So that's what it looks like when we walk up to it. Everything I already covered except for this. A lot of the airframe is carbon fiber. So to receive transmission, we couldn't have antennas inside carbon fiber because it acts like a Faraday cage and blocks all communication. So we wrapped the vehicle with a kind of homemade antenna, which ended up working great. So that was interesting. So everything, we have kind of video evidence up to us lifting up of everything working autonomously. This is kind of before we got to the field. So you can see this is the main camera. It goes from being 90 degrees off to the side up to the top, just like we want, which is great. And then the lift, you can see this is a picture before. So this is kind of why the motivation for the lift system. We're kind of flush up against the body, and any pictures you take are going to be 50% rocket, which is not very interesting. If you're on another planet or something like that, you want your landscape. So after we lift, that's kind of reduced to that little fraction of the picture. And then these are the images that, so this is where I'll talk about our issues, I guess. So we had done a ton of testing, lifting, coming up and down, and it got the pictures every time. But then on this day, what we hadn't tested was in like the Huntsville heat. So the rocket, basically NASA puts it on the pad and then they shoot off a whole volley of them over the course of an hour or so. So it sat kind of in the baking in the hot sun. We got a black rocket, which is not the best idea now. So the internal temperature in there got up to like some, I don't know, 60 C or something like that. And our primary controller fails or starts throttling and monitoring itself at around 80 C. So we were already right up there. And then if you kind of go back and look at our logs, our temperature was way too high. And actually so it did all this autonomously, which was great. But then when it went to take the pictures, basically all of the USB connections. So even though we had 3 redundant cameras, so each one can work and save the mission, all of the USBs disconnected because the USB hub basically overheated and failed. So we got there, we kind of logged in, saw that we didn't have pictures, and we didn't have to fiddle with anything, but we just restarted the computer, gave it a sec to chill out, and then autonomously received and took the pictures. So it's still, all the hardware and the mechanical system still functioned and had the capability to function, but it was a overheating issue that had been overlooked. And there's been some instances of that with like NASA projects of they need to flip to the B side of the programmer and do a remote reboot and get something working. So like software glitches are recoverable, but in our case, it was a software fix for kind of mechanical oversight of thermal issues. But that being said, we turned it back on and it immediately started swiveling around doing its thing. So we got a couple pictures and should have taken some more because the first one, just as the camera turned on, is overexposed.
So, where did y'all launch it? Is it in the Redstone Arsenal or at some deer hunts?
It's a brag farm. It's called just a private farm that I guess NASA pays the farmer for the day. And they set up. So
there is life on this planet.
there is life. Yeah, we found some
It's
alien.
amazing you landed that and you didn't get any of those people.
Yeah. Thread the needle. Yeah, so tough lessons to learn, little heartbreaking because especially from a distance, everything looks like it goes perfectly. But something our professor always said from the start, and it always kind of annoys you, but I don't know, you grow wiser, was like failure, like NASA's slogan in the 60s and all that was failure is not an option. And his thing is failure is not an option, but failure is assured. You have to basically, failure is going to creep its way in through every small crack. You think you checked 1,000 boxes, and then it's the 1,001 thing that gets you. So we did overall, I think it was like 10,000 hours into the project between a pretty small team of 10 or 11 people. So pretty brutal lesson to learn at the end. This is a plot of after we got it back, we stuck it in a hot box and kind of ran our software to see where the issues were and kind of confirmed the temperature issues. And that remote reboot that we did, the whole mission could have been saved had we just added kind of one more check in software, and then everything goes perfect. So obviously hindsight's 2020. That's not like a what if, but it's more of like the attention to detail that you need and the level of thought that you need, whether it's one team using metric units, one team using English units that can destroy the mission, or a piece of foam on your heat shield that ends up causes the loss of life. Basically, every little thing can get you. And that's kind of the main takeaway and what we're all grateful for and why we put in all those hours and want to do the project like that is to get kind of the full systems engineering approach. Pretty much everywhere you go to NASA, you go to Lockheed Martin, SpaceX, you're a small player, unless you're Elon Musk, something like that. You're a small player, you work on one subsystem, you're either on the structural team or the fluids team or the electrical team, and you're working on one component. So it was a super valuable experience for everyone to get like a whiteboard to product. Everyone can tell you every inch of that rocket and how everything works, which is awesome. Like I said, kind of all the lessons that one associates with failure. So overall, we came in third overall. So not first, not last, but still a failure in our books. And basically just overall gratitude for like things that just work every day. Like every day you get in your car and it just, for the most part, just works. NASA pulls off these insane missions year after year, and kind of how much that takes, then the level of brain power that those people have and dedication is pretty remarkable. The communication stuff, it's all basic project takeaways, but everything from youth outreach to fifth graders, stuff like this, and then NASA makes us write like 3 250-page reports throughout the year. So technical writing, and then you have to present to them, all that kind of full spectrum communication. It's good practice that, especially engineers, you don't get a lot of class presentation time. Pretty much all book work and tests and things like that. So it's nice to get some presentation time. And then conflict resolution, there's small team, thousands of hours being put in. Obviously, there's some friction that takes place. So just learning how to navigate that and work with people from different backgrounds, different strengths, and just appreciating that basically, I would say like every person on the team, there's 10 of us, 11 of us, at one point or another kind of puts the team on their back and carries and pushes everyone through, and learning to appreciate that in your team and how valuable every individual is. If one day they're pissing you off and the next day they're saving you. So you learn that lesson over and over again, which is special. Yeah, and then student outcomes. So we've been doing this for 16 years now. And obviously I'm still at Vanderbilt here. But all the alumni, they come back and visit all the time. They hop on our Zoom calls and help us talk through any issues, which is super helpful. And very, very tight-knit network, which is incredible. And they've gone everywhere. Some, obviously, not everyone's still engineering, but pretty much everyone goes and works in industry or goes to grad school right after. Because you kind of realize that it's like college and right after is kind of the only time you're never going to come back to engineering if you leave for 10 years. So people go and work at incredible places and do cool things. So grateful for that network. And yeah, regardless if you engineer or if you end up in consultant or whatever it is, I think like the universal skills everyone learns has been valuable. That's about the end of mine. So I've talked for so long, but they can hop in on. They just have 2 quick slides on their project, and happy to take questions on any of it, obviously.
So let's be updated. So has everybody seen videos of any of the missions to Mars, any of the rovers that goes on? There's like many different parts of the mission. Like first, it has to arrive to Mars, and then it has to deploy the parachutes. Then it has to deploy the retro thrusters, and it has to land smoothly on the ground. And then the actual like box or whatever the rover is inside has to open, and the rover deploys everything. So it's a bunch of different processes that happen one after the other. So basically, this year's project is something kind of similar to that. We have to be able to eject something from the rocket while it's still in the air, and that the thing that we eject from the rocket has to land smoothly on the ground without using parachutes or streamers. And so it sounds broad, because basically NASA gives us the option to innovate, think how can we basically approach this project. And then we have many different options at the beginning. At the beginning, it's always like a very messy process because we need to brainstorm quickly. What are we going to do? Right? We have a bunch of ideas, and we have an idea of using an airbag to deploy airbags in the air or right before we touch the ground. We also had an idea of using cold gas thrusters to slow it down in a slowly manner, but then we figured out it wasn't enough to slow it down. It would be too risky to have a pressurized tank there going down there. It might explode, right? So there are a bunch of issues related to that. And then we also came up with the option, probably the most obvious option, which is using a drone and like a quadcopter. But then we figured out maybe that could work, but it's also probably every other college will be doing the same. So if we want to win, we want to do something more complicated, but not necessarily more complicated, but more challenging and more innovative than a quadcopter. So I don't know if that's
We're gonna say USB
okay.
here real quick, yeah.
What's there?
Yes.
Slides that updated in the afternoon after I saved my flash drive.
So while we are waiting for this, and I guess also something useful to share will be like everybody in the team. I mean, it's very time consuming, very challenging and everything. And to get like a group of people to actually commit that amount of time and effort to that, it's hard. But the fact that we can do it is because every individual in the team is very passionate about it. Everybody has some like childhood story or like some sort of like event in their life that led them to like develop this passion towards this space science. And I'm pretty sure like the astronomy club you guys have is also one of those things that you never know, like there's only one kid that comes or something and then you know they decide their career after that. They say, oh, I want to.
Yeah, meantime, any quick questions? And then,
Back to what was your pivotal moment prior to?
Ooh, well, that's a good question. I think, well, actually, I'm pretty sure about this. When I was in high school, I started flyer about an astronomy competition. It's called Latin American Astronomy Competition, and I was like, oh, I wanna. Like, I always like astronomy. I always watch a lot of videos and read like documentaries and Discovery Channel, all that. But I never really took it so seriously to actually do something like extracurricular about it. But I was like, okay, I should give that a try. Why not, right? I didn't feel like I was particularly, I don't know, smart or like competent in math or astrophysics or whatever, but I like it. Maybe I'll give it a try. Let's go, right? And then I signed up. I participated. There was a lot of like there were exams and I was astronomy, astrometry, astrophysics, how to locate stars, how to use the celestial coordinates, all of that stuff. And then I was incredible because I didn't feel like I was studying. It wasn't like a sport. I actually enjoyed doing that. I was like, wow, I'm so nerd. I didn't know this was really cool. And then I ended up qualifying for the national competition. I met people from other countries. They were all passionate about astronomy. They all went to careers in physics or in astronomy. I myself was more of a hands-on person, so I wanted to do more like something engineering, but also still kind of as close to related to astronomy as possible. So mechanical engineering geared towards aerospace was where I found my niche. So yeah, that would be it. Thanks for the question.
Get this list.
Yeah.
I don't know, this, if you want to share what's your.
Yeah, for me, I think it was also in high school, but it was mostly from SpaceX. I saw one of their flights where they landed for the first time the rocket, and I didn't know, I had no idea what I'm measuring, but after watching that video, I was like, I want to make something like that one day, or like work on something like that. So that's when I decided to go into mechanical engineering, and because of that, I was like, I want to go into something space related, and this was one of the like more popular space related labs at the university. So like, you know, I tried to focus really hard to make sure, you know, I get to work on this project on my senior year. Yeah, so explaining a bit about the mission for our year this year. So as Sebastian was saying, we basically have to land a payload on the ground from specific heights, and has to land safely and slow down safely enough that if theoretically you had people in it, they will survive the impact. So that like the slowdown, it has to touch ground softly. You cannot just like throw it, but also you cannot use any sort of like parachute or like streamer, any conventional like so parachute or streamer are prohibited, but everything else is allowed. And so what we decided to do, apart from like setting all those different ideas, is have a mission sequence where we place our payload on this nose cone section. So this is entire part of the flight all the way until 4. This is all going to fall under its main parachute after it reaches its highest points. And then that nose cone section will separate from the main section. And as it's falling down for like a brief 1.2 seconds, 2 rotor blades will deploy. And so this drone will become a uniaxial drone, so it's like almost a helicopter without like the tail section. And then it will slowly come down and touch the ground. And that's how we divide our mission sequence. There's parameters that NASA gives us every year. For example, the reason that the separation has to occur around 550 feet is because they limit us from using energetics below 500. And our separation system that we had to design has to use energetics because we felt that was like the more reliable way to separate rather than rely on a mechanical system that will have more failure points. And so that's like our mission sequence for the year.
I mean,
Yeah.
we can go back a little bit, yeah. Yeah, after we launch and then we at some point start to the nose cone deploys, so it detaches from the vehicle, right? Then you see the rotors being deployed. And after that, and it should like autonomously slow down and then touch the ground. Ideally at close to 0 feet per second. And yeah, that's why it's called 10 knots. Like those are the analogs for astronauts. And that should be part of the challenge. Actually, we have to physically put some like an analogous to a cabin or some sort of like capsule where the 10 knots should be located inside. So that's actually part of the feasibility in there. Yeah, exactly.
Yeah. Basically a big egg drop. Yeah.
So this, okay, yeah. So this is a motor, actually. So it's motor powered. Yeah. So it's like these are propellers. They deploy straight, and then this is a electrical motor. We have a battery inside. We power the motor. We'll have our EE team will work on the control algorithm to make it like time based, so that like we can hit these velocities at specific times and heights, and then finish the landing softly.
And then on the next slide, you can see the.
How do you know what height you're at? Do you have a sensor to tell you?
It's a very good question. So we have so part of the competition was to make our lander to be as atmospheric in the planet as possible, which means we should be able to use it in other planets. And so instead of using instead of using like a barometric altitude like meter, and which depends on the atmospheric pressure, we decided to use a LiDAR sensor on the bottom. So basically here, and there's a LiDAR sensor which works with laser. Right? So just like measure the time that it takes for the laser to bound from the Earth back to the sensor, and then based on that time, then it tells the computer.
When they know how fast to go and so on.
Yeah, you can alternate that with
I
the.
hope it's a clear.
Yeah, ideally.
That was actually part of the issue. I think on NASA's they wanted to use LiDAR, but it was like on Mars, the dust they kicked up from their helicopter messes with your ability to use that. So it's a good point.
It's a good point too.
Back in my day, flying at 15 and 16, our test for if we were successful is we flew eggs.
Yeah.
Oh, yeah.
All eggs. Crack the egg.
Bad recovery.
In what like vehicle was it?
Homemade, we built rockets probably, I would say we got about 4,500, 5,000 feet.
It's pretty insane.
Prayers.
Yeah.
They ever come back in one piece? Yeah.
In orbit.
Yeah.
Yeah. Probably or 7 months.
4,500 feet. Crosswind problem?
Little bit. We do some modeling of that, of just like atmosphere amplification of wind. But we don't have to worry too much. NASA has a basic like drift radius on this field where we launch, and they set your altitude range between 4,000 and 6,000, and we basically want to just get over that minimum so that you don't risk drifting for miles. We're pretty close to a highway there. So to minimize that, that's why we use 2 parachutes. I don't know if you did the same, but there's like a drogue chute, which is super small. That's number 3 there. Super small. It basically just prevents terminal velocity, so you don't have like a missile coming down. So you split open the rocket, you're in 2 pieces now. So you fall pretty fast, like 90 feet per second. But that prevents a lot of the drift with the wind. You don't get taken by the wind. Yes, yeah.
Because it seemed a whole lot simpler to just scoop comes off and just sever that bad boy and let it go, and then take over the LiDAR.
So what do you mean exactly?
He's got a new idea. What? You get up, pop the chute, have it on a timer, and then once your LiDAR kicks in, just jettison the chute and the top part of the rocket, and then just come down with the payload.
Yes, yes. So the reason they set this altitude is they have a safe because there's a big like crowd at this event. So they have to manually like push a button and say detach. Yeah, exactly. But that is how it should be done for like to have the most probably.
Everywhere.
Yeah.
Yeah, and how many people do you see?
We're getting there. We're getting there.
Yeah,
We got one more slide. Yeah.
Yeah, there's one more slide. So this is the computer like design of everything. This is the whole vehicle, the whole rocket. As you can see, the nose cone, the part that's gonna be detaching from the vehicle, it's here, and then you see the rotors are folded out in this direction, inside a protective tube. So after it detaches, it has a mechanism that is designed so that it will immediately deploy the four rotors. And this is how it's gonna look like as it's going down.
How big is that?
It's like eight.
Yes,
That's about 8
yeah. It weighs right now we're like at 9 pounds. And then for total length, I want to say yeah, like 10 inches, something like that. Yeah, and 6 inches wide.
And then wingspan, are you guys doing 18 or 24?
20,
Uh,
so far 24.
24 inches rotors. So this
The wingspan.
the wingspan from here, the diameter of this is 24, and the diameter of the payload itself is 6.
60.
Yeah.
Yeah. So that's one benefit, like with NASA challenge with the atmosphere independence was against a quadcopter design, because if you try to send a quadcopter to Mars, you basically have a limit on how big your propellers can be, because you have 4 of them and they're gonna start hitting each other. So that's why NASA went with coaxial design on their Ingenuity helicopter. So that was kind of with just one rotor, you can make your propellers as big as you want and just flop them out, which is nice.
And then one of the I think is here is where the cabin or capsule of the stenouts go. So this is a physical thing. It resembles like a housing unit.
And what is this supposed to do when it hits the ground? Or gets to the ground, excuse me, gets.
When it touches down.
When it touches down, it's the ground. Just nothing. That's it. Like
The motor is gonna be installed immediately.
Yeah.
And then ideally it will touch the ground at 0 feet per second. So it'll be a very smooth landing, and then the rotor stop and it's gonna turn.
That'd be sweet.
Shoot out some fireworks.
That'd be awesome.
Yeah.
That's pretty much it. If you have any questions, let us know. Obviously, I mean, you talk to Andrew, so but you know,
Yeah.
we're happy doing outreach events. Probably as the year progresses, like now it's like still theoretical part. But as the year progresses, we'll be like making hopefully like next year one of us will come back and present on you all in details like Andrew did of our project. Yeah.
First place.
Yeah, hopefully, yeah.
When do you guys launch? When's the official date?
It's in April. Like actual competition is in April. I think 15.
Yeah.
And next year. But we have to test and do like test and launches.
So say, do you test around here? Or do you have to go?
We go to Kentucky usually.
What are some of the other teams' approach to how they solve this?
We don't know, but we can guess. We have meetings with NASA where people ask questions. But a lot from the questions, a lot of people sound like they're doing drones.
But we
So
don't know what kind of drone.
Yeah.
Maybe it's a quadcopter.
it's,
Yeah. We
Yeah.
don't know exactly.
uh,
So yeah, it's like a secret. So guys, please don't. Don't ask them any questions. Yeah.
So now you have experience with NASA, but you're also inspired by like SpaceX and Blue Origin and Stratosphere. If you had your choice, would you go with a private contractor or would you stay in the government?
I would personally go to SpaceX.
Yeah. Yeah, that's it.
Exactly.
But do you think it, like the benefits of reusability or just the size they're working at, what would draw you?
I think, yeah, for one hand, innovation is like a lot more. I mean, the rate of innovation of SpaceX is like higher than any other space company probably in the world right now. that and also for the more high paying, my high paying system. And also the project actually progressed in a more like fast than the NASA project, because NASA is a public entity at the end of the day. They depend on what funded. And once the politicians, they have different goals in different administrations. So NASA, it doesn't, I mean, it can go through the same project. Maybe someday they're like very, they're almost like finishing a project, but then they have to complete this card if it's not like what the Congress want anymore with that. So whereas the SpaceX, it's like they can do whatever they want. Because they have a private companies where they have money, they can test, they can destroy the rocket as many times as they need. But for NASA, it's like, oh, we can destroy our rockets, like bad image. People are gonna complain, oh, what are they doing with my tax money and things like that. So, but SpaceX, they can do whatever they want. So
That's not the way it used to be. It's like it's always blue. On television in front of everybody.
yeah.
They got away from it.
No, back, when we were shooting our rockets, we thought we were hot stuff. We bought a camera. And I guess it was a little bit bigger than my phone, okay? And it used 110 film canister. He's over there going, oh, you know. And the deal was when we shoot the rocket up, and then when it would flip over, that's what clicked the shut.
That's cool.
And then it would come back. Pictures, we got pictures back. I mean, and you really, yeah, that's a tree.
That's pretty cool.
Hey fellas, you said you used commercially available rocket motors. What size motor did you have to use for your craft?
Size F. Wait,
L.
oh, sorry.
L motors? Or was it
Yes,
one
L.
one L motor?
Yes, just one, all single stage. Yeah.
Okay. Neat.
I think L is the maximum. Most teams use either K or an L.
K or an L.
Yeah.
Nice.
Yeah, we also have test launches where we do use K as well.
Yeah.
For the smaller.
C and D was the big back in my, a D engine, man, Kings running a D engine. No, we had a little transponder and we were, when I grew up out in Georgia, the first thing that you've never heard of, but there was a radar base up there, which we've been out there forever and it's just a bit couldn't go on. Yeah. But we were out in the field, we were shooting around, we had a little transponder out, you'd see me here. And all it did was go beep, beep, and it was hopefully so we could find it. We could reach it off. We had a little radio and we and me and my two friends were up there on Saturday afternoon. I started kind of playing rockets. And these guys, military looking guys, came floating across the field in a Jeep. And these were, I had a feel, what could we be doing? And so they took us in the Jeep and took us to the radar base in our rocket with our little beeper on it. And it turns out that whatever frequency we were on was blanking out ATC for most of the southeast United States.
No, that's air route traffic.
Yeah.
And it was Air Force early warning.
This was instead of coming in very feeble, but and he was like, let me show you what you do with the radar. And we turned on our little thing, and it just went white. Oh, we can use this one.
Give you a job.
Yeah.
You get busted.
Yeah.
You get busted.
Spies.
Yeah.
Just wanted to know what was crapping out their system. And we were only putting out a quarter of a watt, how bad could it be?
Yeah.
Well, it's because it was at 4,000 feet,
Yeah.
things amplify real quick.
They probably have hypersensitive equipment too.
Yeah.
All that stuff. Yeah.
600,000 yards away.
Yeah.
Yeah, we.
Show me the video though.
Oh yeah, the
Yeah.
launch.
Sure.
Are there other labs on campus that do these competitions and stuff as well, or?
Specifically this, not really.
Yeah.
There's a club called Satellite Club, and where they do launch high altitude balloons with some sensors.
Gotcha.
But yeah, so, like high power like devices, no, only yes.
Most labs.
You just did play or launch presentation. Just come up.
Let me ask my question again a different way. Your rockets you set up that came down and the little camera popped up, what were some of the other teams? How did they address that problem? Because you did get to see them, right?
Yeah, I mean, I guess Andres one was there.
They use that liquid nitrogen cooling system so they didn't overheat.
Yeah, I think bigger heat sinks on your processor honestly would have just done the trick. Nice and simple.
But did they,
Yes.
I mean, did they all come down and.
Oh, like other approaches to the thing. Yeah. They had a lot of teams do this kind of thing where the rocket, and we thought of something similar. It would basically pull apart in the middle. It's like we'd attach our parachute and then that was just our payload. So they had like their payload sitting in there. Their rocket would split apart to expose the payload. No lift or anything. So 50% of your picture would be the inside of your rocket, like when you look to the left and the right. But then it was kind of like a beanie bait, not what do you call it? Those mighty beans that don't fall over. They had these like bottom heavy things that could swivel. So it was bottom heavy, the camera would swing up and then spin around. None of them worked too well. The simplest approach is that we went back and forth on this as a team so many times of the simple thing that works versus the cool thing that's riskier. And we went for the cool thing that's riskier and messed it up. But the thing that won, nice, simple arm, stick it up there and spin it around. More rigid, easier to. The main issue with ours, with extending something like that, is all the wiring, because you need wires going to the top for your swivel motor and for your cameras. So you have something, you need all those wires compressed in here, and then have them not get caught in anything, have them stick out, and still have the degree of freedom. Exactly. So that was not an oversight, like we considered it and just kind of assumed that we would figure out a solution, but there's kind of very limited solutions with that. Whereas you stick out an arm, you can swivel your whole platform that thing is on, which is nice. But yeah, I would say the only thing that was better was just a simple design. But there's some bottom heavy designs, and people had nothing, no elevation, but they had like a little bubble, like a viewing bubble on the side of their rocket, and their camera was always in there and spin around, but you get a lot of distortion from like just being inside of a bubble. So the pictures weren't that great. But yeah, ultimately not a ton of solutions. It's kind of one of those things, and their product is similar, where you see a vague challenge and you think there's so many ways to tackle it. But then when you really think about any of them, there's two viable ways really. And maybe just one, and that's what wins, which is kind of cool.
What's the prize?
Prize, I think you get like the school, not the students, but the school would get like 10K or something. The bragging rights, and then that's about it. Oh, we got some shirts, we got some sweatshirts. Yeah, we got the swag. Yeah, got the pictures. But yeah, nothing concrete. I think the video, I'm not gonna make you guys watch this whole thing, and I don't think I can fast forward. So it's all right. But yeah, we just got some fun rocket launches.
2 minutes.
Yeah. Play. That's good. We had to do like a project video for senior design, basically. And
You make it full screen?
no.
No, really?
So
Vanderbilt campus still had the Starlink problem in the spring. You could use that to.
Yeah.
Scatter them off. Yeah. Now they have these artificial birds now.
Yeah,
It's insane.
They had these cannons. They shoot these, I mean, honest to God, and every now and then you just, boom.
Yeah.
And, somebody was, who they were, but we were standing out there waiting to get on the show, go home, and booze going off from the truck. And we went, well, just one of the PhDs didn't make it.
Year 5.
How many iterations of rockets? You know, you mentioned all those units of failure, those points of failure.
Yeah.
Like, how often do you just have to go,
Scrap it.
yeah,
Honestly, not too many times. There's a couple like throughout the year, probably like 3 like major crises where you just realize you overlooked something like the wiring or something like that. But the first like month and a half of the project is just design pretty much. So ideally never.
how are the rules in terms of like revisiting one of your previous designs? Like, do they limit that and like they go, oh, this is this lab? They have
like
this-
year to year.
Yeah.
Yeah, you're not.
Yeah, you're not allowed to copy like from like so excessive. They say excessive copying from previous like years is like penalized basically, and so you cannot copy like in the reports or reuse like designs. You have to do something new. But you can rely on experience. Like if you know the motor, like the same motor works well. Like we know this curve. It's very consistent. We usually go with the same company, same motor. Especially if it works for us, rather than like getting a motor with the same specs from a different company, because we tested those motors so many times. And then for iterations, the full rocket, like so there's like a subscale flight, which is like a smaller rocket to prove that we can actually fly rockets, and then like the bigger flights where it's like the full scale. The rocket by itself like doesn't change much, and there's like times, for example, we have a deadline next Thursday where we lock in our like main design. So after that, if we do anything major to the design, NASA would be like, okay, like why? Like, because you had all this time to design, why you're changing this best. But small things, like for example, separation mechanisms, like that you can iterate on really, really quickly and have like 4 or 5, 6 versions. Still works similar ways, but then you're like, oh, the tolerance on this was not good, or like I need to add a pin here, or like I need like something else different, or the thickness is not right. So those small things, yes, but like eventually the full design you cannot iterate on as much. Like starting in November, you're like locked in. The bigger reports have to be like proving that the design you chose and the design actually works. So that.
Thank you.
Yes, thank you guys. Thank you for having us.
Nice fellas.
All right. Well, does anybody have any further questions for our group while we're here? I know there's some people on Zoom trying to get my Zoom back on for some reason. Let me stop the share. There we go. Does anybody have any questions on Zoom? I think I saw a comment somewhere, but I think it might have gotten cleared. All right. Well, if there aren't any other questions or comments, thank you everybody for attending in person, online. Thank you, Vanderbilt Rocket Team. Best of luck coming up, next week, I guess, Thursday, right? You have to get your design it. But feel free to shoot us a line and let us know how you guys are doing. And if you ever want to get some more outreach, we'd love to have you guys get an update on how you guys are doing. So if anything, we'll bug you in April and see how you did.
Thank you.
Good.
Thank you for having us.
Yeah, of course. Thanks, guys. All right, with that, we'll go ahead and adjourn today.
Thank you, Tom. Thanks, Tom.
Yeah, of course. You guys have a good day online. I'm gonna go ahead and shut off our Zoom screen. Feel free to email me if you guys have any questions on anything, and I'll hopefully see you guys at the next star party. See you guys.
Yeah. See you soon, Tom.
Yeah.